Okay, there are a lot of important topics in Calc 3, um, and this is probably one of the two most important topics that we'll talk about this semester. Important in the sense that um, this idea that we're about to go through of finding maxima and minima of functions of several variables and using the first derivatives and setting them equal to 0 and so forth. This is something that pervades applications in math, in physics, in chemistry, in economics, in just so many areas. And the ideas that we're going to get a glimpse of here, you could fill a whole graduate program in just maximizing and minimizing functions of several variables. There are amazing, beautiful theoretical techniques that are still currently being developed. There are computational methods for maximizing and minimizing functions that are still actively being developed. Um, I really can't say enough about this. Let's say you're running um, you're the you're someone that runs UPS, the delivery company. Um, you have all of these various cost factors and so forth. And what you want to do is optimize your costs, optimize your expenses, um, so that you can maximize profit for your shareholders or what have you. And that's all the way from the kinds of materials you use to put boxes in, to the kinds of trucks that you use, to how those trucks are driven, what's the shortest route if you are a driver and you have 400 packages that you need to deliver in a particular city. What's the quickest way to visit all of those places where you need to drop those packages off? These are all very challenging mathematical problems, and they are all still actively developed. And the people that develop and research these problems at places like UPS, Walmart, Boeing, the people that research these are all PhD mathematicians, and they are all extremely well paid by their organizations because their organizations understand that, for example, if I work at UPS and I come up with an algorithm that uses just that much less fuel, 1% less fuel in a given year, we're talking about millions of dollars. So that person's salary has been paid for 100 times over, and mostly what did they have to do? They just had to sit in a lab and do some computer modeling and think about setting first partial derivatives equal to 0, among other things. So that's my pitch. This is a very important topic. The other really important topic will come at the end of chapter, let's see, chapter 6, and that is really the culmination of a lot of the work that we'll do this semester in the form of the divergence theorem. So the divergence theorem and integration, hugely important mathematical idea. And here on the derivative side, maximizing and minimizing functions of several variables, hugely important topic, still very actively developed to this day. All right, the big idea is, look, we'll just compare and contrast this with Calc 1. We know how to find the maximum and minimum of a function in Calc 1. You take the derivative, you set it equal to 0, you find the critical points, and you search those critical points for maximums and minimums, because you know that if a function has a maximum or a minimum, it must occur at one of these critical points. And then there's also the boundary question. So if you have a function, let's say it's defined on the interval from 0 to 4, you're of course going to look for critical points and look for maxes and mins that occur at those critical points, but you're also going to have to check the endpoints, because the derivative may or may not be 0 there, because the function is essentially just cut off at those endpoints, but the function might achieve its highest value at that endpoint. So you have to kind of separate the two problems. There's looking for critical points, maximums and minimums inside the domain of the function, and then there's looking for maximums and minimums on the boundary of the domain. And we have that same dichotomy here in functions of several variables. So what are we going to do? We're going to take the partial derivatives. Instead of having one derivative, now we have two partial derivatives, two first partials, or three first partial derivatives, depending on how many independent variables they are. But what we're going to discover is the places in the domain of the function where all the partials are simultaneously zero, those are the critical points. And even better, if we're looking for maximums or minimums of the function, we know that we can just limit our search to those critical points. So setting derivatives equal to zero, solving those systems of equations, that's what we're about here today. As in Calc 1, where there was a second derivative test, we knew that if the second derivative at a critical point was, say, positive, then we knew that that critical point was a local minimum. And if the second derivative was negative, we knew that that critical point was a local maximum. We have a similar test, although a little bit weirder here in Calc 3, and we'll talk about that second derivative test in this section. The big ideas here, again, just to repeat, like in Calc 1, the search for extreme values, maximums and minimums, are going to be, will be focusing on critical points, places where all of the first partials are zero simultaneously. The book doesn't say this, but another way to think about it is we studied the gradient in the last section. And remember that the gradient is the vector of first partial derivatives. So if you want to use language that's even more like Calc 1, critical points occur when the gradient is zero. What does it mean for the gradient to be zero? It means that the vector of partials is equal to zero. What does that mean? What does it mean when a vector is equal to zero? It means each of the components is individually zero. What does it mean when the gradient vector is equal to the zero vector? It means each of the first partial derivatives that appear in the gradient is zero at the same time. That's the kind of point that we're looking for. Those are the critical points. Not every critical point is a maximum or a minimum, and we'll discover that. And then we will also discover that the critical points help us find maximums and minimums on the inside of the domain, but not on the boundary of the domain. The challenge here, what's kind of new, is in Calc 1, the boundary of the domain, say the boundary, let's say a function had domain 0 to 4. What's the boundary of that domain? It's a pair of points. It's the point 0 and the point 4. And checking that boundary was relatively easy. We could just take the 2 points, put them into the function, and see what we got. If the values were higher, then one of them was the maximum. If the values were lower, then one of them was a minimum. That kind of thing. Some things to watch out for in this section. The algebra is a little more challenging than it was in Calc 1 because you're looking at a system of equations. You want the partial with respect to x to equal 0, the partial with respect to y equals 0, partial with respect to z equal to 0. 3 equations, 3 unknowns, or in the case of 2 variables, 2 equations, 2 unknowns. So you're now faced with the algebra of solving those kinds of equations. And I want you to pay close attention to some of the examples that I work here at the end of the lesson, because it's an exercise really in logic as much as it is an exercise in algebra. And I want you to pay attention to the logical approach that I take. Okay. Let's look at the textbook here and look at some of the definitions and some of the examples before we go on to work the exercises at the end of the book. The critical points, yes, we're going to have critical points in Calc 3, just like we had in Calc 1. The critical points for a function of 2 variables are those points where the partial derivatives are simultaneously 0. And for a function of 3 variables, exactly the same condition, except we have f sub z, and more generally, really what we're looking for is places where the gradient is 0, the gradient being the vector of first partial derivatives. Critical points are important because they limit the places that we need to search to find maximums or minimums. If a function is going to have a max or a min inside its domain, inside, not on the boundary, but inside, if it's going to have a max or a min inside its domain, then it's necessarily going to be the case that the gradient is 0, so we can just limit our attention to those critical points, the places where the gradient is 0. Finding critical points, let's look quickly at example 438, and let's look at part B, probably because the derivatives are a little bit easier. So in part B, we've got this function that's essentially a polynomial in x and y. And we're going to look at the partial with respect to x, partial with respect to y. So those are given here, partial with respect to x, partial with respect to y. In this particular case, we get two equations. When we set them equal to 0, we get two equations and two unknowns, x and y. This happens to be a linear system of equations, and so we can do kind of the things that we learned about in algebra to solve this system. In this case, probably what I would do is subtract this equation from this equation to eliminate the 2x. Then I'd be left with an equation in y that I could solve, and then I would return to one of the equations and substitute that solution in to figure out what x is. And what we're going to discover is that the partial derivatives are simultaneously 0 when x is -1 and when y is -1. Now, that doesn't tell us whether there's a max or a min here, so we have to go further and think a little bit about whether it's a maximum or a min, and we'll deal with that at a later point. All right. Before we can talk about classifying critical points as either local maxes, local mins, or neither, we have to understand what a local max or a local min is. We're going to say that f has a local maximum at some point in its domain if all of the values of f near that point in the domain are less than or equal to the value of f at that point. Let me see if I can make some space here. So definition of a local extreme. Yeah, sorry about that. I want my space about right here. Okay. Give myself a little bit more space. Yes, this is me fumbling around with OneNote. All right. You have a point x naught, y naught in the domain of f. And we can say that there's a local maximum here if there's a little circle, and I don't really care how big it is, just so long as a little disk around this point exists. It can be as small as necessary, so that every point in the disk, x, y, gives function values that are less than or equal to the function value at the center of that disk. That's what we mean by a local maximum. Similarly, local min, can we find a little disk around x naught, y naught in the domain so that all the function values on the disk are less than or equal to the function value at the center of the disk? That's the definition of a local extreme. Once we have that, we have Fermat's theorem, which says that if f is differentiable and has an extreme point inside its domain, aka not on the boundary, then the first partials are all 0 there. So this is a necessary condition, and it lets us limit our search for extreme points to places where the first derivatives are all 0. Okay. Here's a nice example of sort of a limited domain. Here's the upper half of a hemisphere of radius 4. Z equals the square root of 16 minus x squared minus y squared. Now, just geometrically, we know that the maximum value of this function is going to occur here at 0, 0. If I plug in 0, 0, I get the square root of 16, aka 4. Now, if I move away from 0, 0 in the domain in any direction, I'm going to fall off of that peak. The function's going to start taking values that are less than 4. And all the way out to the point, if I get out to the boundary here, where x squared, where xy lie on the circle of radius 4 in the xy plane, z is actually going to drop down to 0. And in fact, this function is not even defined outside of the circle x squared plus y squared equals 16. So here's a function of two variables that has a very limited domain. The domain of this function is the circle of radius 4 and its interior. And the maximum of that function occurs at the origin. Now, if you took the first partials of z with respect to x and with respect to y and set them equal to 0 and solved, you would find one solution. X equals 0, y equals 0. That would be a critical point. We wouldn't know whether it was a max or a min without testing it, but we can see in this case that the critical point will occur at the origin exactly as we expect. Where's the minimum of this function? Well, none of these points on the interior are going to be minimums, but any point on the boundary of the domain will be a minimum of this function. So z has a lot of minimums and one maximum. The minimums all yield the value 0 because z is 0 all the way around the boundary of its domain. And the maximum will be 4, and it occurs at one point at the point 0, 0 in the domain. So any point in the domain along the boundary will give a minimum, and any point along in the domain, only the point 0, 0 in the domain gives a maximum. Critical points only occur on the interior of the domain, so if we're looking for maximums and minimums, we also need to look at the boundary of the set, and I'll do a couple of examples like that later. Okay, the second derivative test in Calc 3 is very strange, and we're only going to talk about it in the context of functions of two variables, although there is a second derivative test for functions of three variables and even higher. It's wildly complicated, and it's beyond the scope of this class. However, the second derivative test for functions of two variables, it's still useful, and there's still plenty of real live examples where you want to maximize functions of two variables, and so this is a useful test. Let me first talk about what kinds of critical points can we have where it's neither a maximum nor a minimum, and the answer is a saddle point. So here we have a saddle point. It's called a saddle point because it's sitting right here, and you can imagine if you wanted to sit on this thing, you'd have your left leg sort of dropping down here and your right leg dropping down here, and if you know about horses and saddles, this might be the pommel of the saddle. So you're sitting in here, and the reason saddle points are interesting is they have their partials are equal to 0. For example, if we look at the slope of the function in the x direction along this piece, it bottoms out right here at the saddle point, and we can expect that the partial of f with respect to x is going to be 0. And similarly, if we kind of come at it in this other direction, we can see that it's going to top out here in the other direction, and we might expect the partial with respect to y to be equal to 0. And this doesn't perfectly line up with the x and y axes, but that's kind of the idea. And what we see is there's a maximum in one direction and a minimum in the other direction, and they coincide at this saddle point. Because of that, we get the gradient equal to 0. The partials are equal to 0 simultaneously, but they're not in the kind of agreement necessary to get a local max or local min, because if I focus on this point right here, there are points nearby that are higher, and there are points nearby that are lower. So this point right here in the middle, this function value, can't be a max or a min, because arbitrarily close to it, there are values that are above and below. So this is a saddle point, and this is one of the things that you can run into. Okay, here's a definition of a saddle point. It's a critical point, meaning that the first partials are equal to 0. And I just want to note as an aside that there's a typo here. The definition of saddle point here, this should be f sub x, the partial of f with respect to x equal to 0, and the partial of f with respect to y. I've reported it to the authors. Hopefully it'll get fixed in a future edition. So this is the definition of a saddle point. It's a critical point, but it does not have a local extreme there. How might we discover that? This leads us to the second derivative test, which really on its face looks really crazy. And it is a little daunting at first, but 90% of it hinges on being able to just calculate second derivatives. So there's this strange quantity called the discriminant, and it's denoted capital D. And it involves computing the second partial with respect to x, second partial with respect to y, and then the mixed partial derivative fxy, and evaluating them at the critical point. Okay, and there are essentially three possibilities here for D. Either D is positive, negative, or 0. If it's positive, we're in the first two cases. And if the second with respect to x is positive, then it's a local minimum. If it's positive and the second partial with respect to x is negative, then it's a local max. If it's negative, then it's a saddle point, definitively. And if it's 0, the test is inconclusive. We have to resort to some other means to figuring out whether it's a local max or a local min. We'll talk about the second derivative test. We'll apply it in some of the examples. Where does this come from? That's unfortunately a really challenging question. Let me at least give you a hint. Here in part C, I'm going to talk about the gradient and something called the Hessian. So if we have a function of two variables, in some sense the derivative of f is the gradient of f, and that is the vector f sub x, f sub y. The second derivative so the function itself is a scalar. The first derivative is a vector, and the second derivative is actually a matrix. And if you haven't had linear algebra yet, or you don't know what a matrix is, feel free to ignore this. But if you're interested, the second derivative is a matrix, and it looks like this: f sub x, f sub xy, f sub yx, f sub xx. It's this matrix of second partials. Sorry, f sub xx and f sub yy. Got to get it right here. Now, we talked a little bit about taking derivatives of 2x2 matrices when you learned about the cross product. Not the derivative, the determinant. I don't remember what I said. Anyway, the determinant of this matrix, which we'll denote with a capital D, is fxx times fyy minus fxy times fyx. Now remember, Clairaut's theorem says that mixed partial derivatives are equal, so we can go one step further with this and just write fxy quantity squared, because fxy is equal to fyx. That's exactly this quantity that we're staring at here. Now, what does the discriminant or the determinant of this matrix have to do with anything? Just like in Calc 1, this kind of describes concavity. At this point. And if the determinant is positive, then the function it has concavity, right? It's either concave up or concave down. In both cases, right? If the discriminant, the determinant is positive, it has concavity. If it's negative, it doesn't have concavity. You need concavity in order to have a local max or local min. So in order to have a local max or local min, you need a positive discriminant. That's the first two parts of this. So you're only going to get a local max or a local min if D is positive. If D is negative, there is no concavity there. And so there can't be a max or a min, and in fact it has to be a saddle point. And that's what's happening here. There's no concavity here. We can't definitively say it's concave up or concave down here. And the discriminant is telling us that by being negative. Whereas if we go up to this example here and we sit at this point, the discriminant at this point is actually going to be positive, because this function, this surface, has concavity. It's unambiguously concave down. Positive discriminant. once you have that it's unambiguously concave up or concave down with this positive discriminant, then it suffices to just look at either fxx or fyy. In this theorem, they look at fxx. If it's fxx, it's concave up, right? You only have to check one direction because it has concavity, so we check one direction, it's concave up, must be min. Or we check one direction, fxx, it's concave down, it must be a local max, and that's it. And again, if d is less than 0, there's no concavity at the point. It's a saddle point. And if d is equal to 0, we don't really know. We have to resort to other means. Here are lots of different possibilities in this set of examples. Okay, you can review this box for solving, finding critical points using the second derivative test. I'll demonstrate that in a second in the exercises. The last subject might be one of the most complicated subjects, and this is the idea of absolute maxes and mins. You can find local maxes, right? You can find all the local maximums and minimums, but you may not find the absolute max and min max or min because it might occur on the boundary. So finding the absolute maximum and minimum of a function means finding all of the local maxes and mins, in addition to finding the maximum and minimum of the function on the boundary of its domain, if it exists. Comparing them all to each other, the biggest number is going to be the global max or the absolute max, and the smallest of those numbers will be the global min or the absolute minimum. We'll go through that process in a bit also. Here is an important theorem, the extreme value theorem, that says if f is continuous on a closed and bounded set, then it attains its maximum and minimum values. What is a closed and bounded set? Okay, for our purposes, a closed set contains its boundary. And it's kind of the difference between, let's use a circle here. So the circle and all the points inside of it, this is closed. What if I want the circle and only the points inside, and I want to exclude the boundary? This is an open set, or it's certainly not a closed set. I would love to talk to you about open and closed sets for a while. It's one of my favorite topics, but it's, again, beyond the scope of this class, and I think for our purposes, it's enough for you to just imagine that it's a set that contains its boundary or a set that doesn't contain its boundary. And I haven't really even defined what boundary means, but this is a safe way to think about it. What's bounded? So bounded, a set is bounded if it fits inside a circle of some radius. So can I find a circle around any point? It doesn't matter. Can I find a circle of sufficiently large radius that contains the set? So it just needs to be inside some circle. That's a pretty, a pretty broad definition. What's an example of an unbounded set? I don't know. Let's think about, for example, the collection of points in the plane where -1 is less than or equal to x is less than or equal to 1, and y is anything. What does that look like? Let's get ourselves a coordinate plane, x, y, and let's look at the line x equals 1 here, and the line x equals -1 here. Which points satisfy this membership test? All of the points in this strip. Now I'll ask you, is that a bounded set? Right? Y can be anything. Is that a bounded set? Can you find a point and a circle around that point that contains the entire set? The answer is no. Pick any point, draw any disk around it, and there's going to be stuff up here, right? There's going to be stuff up here, and stuff down here pokes out of the set. So not bounded. So a bounded set is one that fits inside some circle. I don't care what the circle is, but it fits inside some circle. So what this is saying is if f is continuous on a closed and bounded set, a set that has its boundary and fits inside of a circle, then it attains its maximum and minimum value at some point in the domain. It's a very technical theorem, but incredibly useful. Maybe not so useful in this class, but certainly useful in more advanced applied math. Finding the extreme values of a function of two variables, you need to examine the interior of the domain and you need to examine the boundary of the domain. And we'll do an exercise like that. And this gray box kind of summarizes the process. All right, I think that's about it. Let's jump over to some of the exercises here. Some of these exercises can be quite long and time consuming, so I want you to be prepared for that. There are a lot of details, and staying organized as you write these things up is really important. So I want you to not only pay attention to the content as I describe this, but also pay attention to how I'm writing things down and how I organize my work. If you mimic what I'm doing, you're going to take advantage of essentially years of experience of me doing this, and I think you'll find it helpful. I'm going to pause right now and take off this sweatshirt because I'm a little bit warm. Okay, an exercise, what is this, 312. We start really with just trying to find the critical points, and honestly this calculation is at the core of all of the work that you'll do in this section. We want to begin by computing the first partial derivatives because the critical points are the places where the first partial derivatives are each simultaneously zero. So we take the partial of f with respect to x. I don't want red, I want black. F sub x. Okay, partial of this with respect to x, that's 4x cubed, y to the fourth, 0, and then minus 16y. And we want that equal to 0. And f sub y, we get 4y cubed, what, minus 16x equals 0. You know, you have a lot of different options when you're trying to solve a system of equations like this. You know, if you can cancel a variable by adding one equation to the other, that's certainly a good idea. That's not what's going on here. It seems like our only option here is to solve for one variable and substitute it, solve for a variable in one equation and substitute it into the other. So let's solve for y in the first equation. We get 4x cubed equals 16y. And continuing, we get 1/4 x cubed equals y. All right, so we've learned that y is equal to x cubed over 4. We're going to take that and put it into the second equation. So that's 4 x cubed over 4 cubed, right? Minus 16x, and that's equal to 0. So now we have to solve for x. Let's simplify this as much as possible. So x cubed cubed is x to the 9th. We have 4 in the numerator and 4 cubed in the denominator, so that's 1 over 4 squared, or 16. Minus 16x equals 0. We'll continue this chain of manipulations by factoring x out of the left-hand side, and let's multiply through by 16 as well. X to the 8th. 16 times 16 is, I think, 256. Or put another way, it's actually 2 to the 8th. That's convenient. All right, so everybody follow that? You factor out the x, and then I changed, remember the 16 is 2 to the 4th, and 2 to the 4th times 2 to the 4th is 2 to the 8th. All right, solving this equation means one of two things. Either x is equal to 0, or x is equal to 2, or x is equal to minus 2. Right, those are the three solutions of this particular equation. Well, if those are the three possible values of x, what are the corresponding values of y? We can figure those out by going back to this equation, where y is equal to x cubed over 4. In the first case, we learned that y is equal to 0. In the second case, we learned that y would be, what, 2? And in the last case, we learned, let's see, negative 2 cubed over 4 is going to be, what, negative 2. Okay, so what are the critical points? The critical points are the solutions of this system of equations. They're the places where the first partials are simultaneously 0. So we have three critical points, 0, 0, 2, 2, and negative 2, negative 2. Now, it wasn't asked for, but what I thought might be useful just on this first exercise is let's go look at a plot of this surface and see what's going on at these points that have caused them to emerge from this calculation. So let me jump over here and go to GeoGebra. Let's go to 3D Calculator, and let's plug in x to the 4th plus y to the 4th minus 16xy. Alrighty, I think that's it. Let me just double check. X to the 4th plus y to the 4th minus 16xy. Yep, that's it. Wow, GeoGebra is really making a mess of this right now, and part of that is we've got these x to the 4th, y to the 4th. These are very powerful expressions. They grow very quickly. So it looks like the scale is not really up to snuff here. In GeoGebra, if you put the mouse along the z-axis and you hold down the shift key and drag, you can actually shrink the scale in the z direction. So when I drag that down, you could see now the z-axis is going from 0 to 100, and we see that the surface is kind of resolved a little bit better for us. All right, well, let's look at what's going on here. You might suspect that there are a couple of critical points here, and you might even suspect that there's a critical point here. And if we stare down from above, you might imagine that those critical points sit at 2, 2 here at the bottom of this thing, 2, 2, and at negative 2, negative 2 here. Again, you're kind of taking my word for it. And then there's another critical point at the origin, 0, 0. And we can actually see that we have two minimums, two local minimums. And what kind of point is this here? It's neither a max nor a min, because there are points near it that are higher and points near it that are lower. So this is a saddle point. So if we were asked to classify, we could look at the graph and we could note that this is a saddle, this is a min, and this is a min. And min means local min. All right, let's look at problem 317. So here we want to find the critical points of the function, and by using algebraic techniques or by examining the form of the equation and verify your results. In this particular case, we're not going to use algebra. We're going to use logic and just look at the form of the equation. This particular function is composed of two pieces, the square root of x squared plus y squared and the constant 1. We might ask ourselves, or we might note here, that this first term is always positive or always non-negative. What does that mean? It means that it's always bigger than or equal to 0. Well, if that's always bigger than or equal to 0, then this is always bigger than or equal to 1, right? And so we might suspect that the minimum of this function is 1. Can we find an x value and a y value that yields that minimum? And the answer is yes. We know that when xy is equal to 0, 0, that f of xy is equal to 1. And since the function is always bigger than or equal to 1, this must be a minimum. So without doing any algebra at all, just using logic, we can reason that this function has a minimum of 1 at the origin. Let's do one that's a little bit more complicated. So here, okay, the directions again, I consider them to be slightly poorly written, and I've notified the authors. The directions say, use the second derivative test to identify any critical points and determine whether each critical point is a max, min, saddle, or none. We don't use the second derivative test to identify critical points. We identify critical points by solving the system of equations that results from setting the first derivatives equal to 0. So in my opinion, this is sort of poorly stated. So we just want to identify the critical points and then use the second derivative test here. To identify each point as a max, a min, or a saddle. All right, if you look at this function, it's a bit more frightening than some of the functions we've encountered so far. And it's frightening because taking the derivative is going to involve a little bit of work on your part. We want to take the partial of f with respect to x, and if you look at this, we can see that there are two functions here. With respect to x. There's 2xy, and then there's e to the minus x squared minus y squared. It's not the only way to split this up, but it's a strategic way to split it up if you're about to apply the product rule, which is what I'm about to do. The product rule says the derivative of this thing with respect to x is the derivative of the first, 2y times the second, e to the minus x squared plus y squared, plus this first, 2xy times the derivative of the second, e to the minus x squared plus y squared. And remember, the derivative of e to the minus x squared plus y squared is e to the minus x squared plus y squared times the derivative of negative x squared plus y squared. So we have an extra factor of negative 2x out here. And that can be simplified a little bit. We have a common factor of e to the minus x squared plus y squared. So I'll pull that out, 2y plus 2xy times negative 2x e to the negative x squared plus y squared, like that. And we can simplify that even further to get 4y minus 4x squared y e to the minus x squared plus y squared. Let me check my notes, make sure I didn't make any mistakes. That looks good. All right, now, if you look at this expression, it's symmetric in x and y. What do I mean by that? X and y, if I were to switch their roles, wouldn't change the function at all. What that means is I can really quickly write down the partial of f with respect to y by reversing the roles of x and y. So just change the y's to x's and the x's to y's. If you're uncomfortable doing that, by all means, just take the partial derivative with respect to y. But I do want you to pay attention to these kinds of patterns. They can save you a lot of time if you notice them. All right, so we have these two functions, the partial with respect to x, the partial with respect to y, and we want to set them equal to 0 and solve the resulting system. This is looking really complicated. All right, is there anything we can do to simplify things? Well, there's one observation that I can make, and that is that this exponential function is not equal to 0. So there's nothing that can happen in that factor that will result in a solution for me. In fact, I can divide it out of both of the equations because it's never zero, and it's safe to divide by things that are never zero. So doing that lets me just ignore those pieces, which yields a somewhat friendlier looking system of equations, 4y minus 4x squared y and 4x minus 4y squared x, like that. But still not quite there. How are we going to attack and solve this particular system of equations? This kind of goes back to the logic suggestion that I mentioned at the outset. I'm going to label these 1 and 2 just because I might talk about them as we go through this. If I rewrite it as 4y, and what's left behind is 1 minus x squared. I feel like I've got a typo in here. I do. Apologies. This is a 2. And this is a 2. 2, 2. So I can pull out a 2y here. Okay, pulling out a 2y, what's left behind is 1 minus 2x squared. I don't need that, I already have it. Okay, and I can do the same thing in equation 2. I can pull out what? I'm sorry, I pulled out a 2y. I'm going to pull out a 2x here. 2x. What's left behind is 1 minus what? 2y squared. Okay, now here's where we have to kind of be careful with logic. Remember that both of these equations have to be true if we're going to find critical points. So let's focus on the first equation, and there's nothing special about the first equation other than that I wrote it first. So we're going to focus on 1. 1 implies that either y equals 0 or x is equal to, well, let me not jump ahead, or 1 minus 2x squared equals 0, which implies that x is equal to plus or minus 1 over root 2. So by focusing on 1, we know that at any critical point of this system, it's either y equals 0, like possibly, right? It can't be anything else. We know either y equals 0 or x equals 1 over root 2 or x equals negative 1 over root 2. These are now facts, right? These are the conditions that equation 1 imposes on us. So in essence, we have 3 cases that we have to treat separately. And what we have to do is try these 3 cases in equation 2. So 3 cases, let's start working through. The first case is that y is equal to 0. What if y equals 0? And let's look at equation 2. Well, then equation 2 becomes, right, remember where equation 2 is? It's up here. What does equation 2 turn into? Well, if y is equal to 0, we see that 2x must equal 0 and that x equals 0. So a critical point, one critical point is 0, 0. Okay, what's the next case? Well, or x could equal 1 over root 2. And again, we go to case 2. We can't go to equation 1 because that's where all of this stuff came from, and if we go back there, we're not going to get any new information. So we're taking these 3 cases from equation 1 and seeing what happens in equation 2. All right, so the second case from equation 1 was 1 over root 2. Let's take that and put it into equation 2. All right, well, we get 2 times 1 over root 2, right? We're replacing x with 1 over root 2. 1 minus 2y squared, and that's got to equal 0. Well, if you solve that, none of this matters. This constant out here doesn't matter because we've set the whole thing equal to 0. And what we discover is that y is equal to plus or minus 1 over root 2. And we've picked up 2 more critical points. 2 more critical points. This one and this one. The case where x is equal to 1 over root 2 gives 2 more critical points. All right, let's talk about case 3. In case 3, we have x equal to negative 1 over root 2. And again, we go back to equation 2, and we substitute it into that equation for x. So we get 2, negative 1 over root 2, 1 minus 2y squared. And you can probably see this coming. This constant has no effect. And so we get 2 more solutions, y equals plus or minus over root 2, and 2 more critical points. Corresponding to x equals negative 1 over root 2, we have 1 over root 2, and negative 1 over root 2, negative 1 over root 2. You really do have to be careful. We have 5 critical points, right? None of these were duplicates. That said, we have found them all with our careful logic and looking at case 1 and acknowledging from case 1 that there are 3 possibilities, and then going through each of those 3 possibilities in equation 2, we get 5 critical points. Five critical points. How are we going to classify them? Well, the exercise is explicitly asking us to use the second derivative test to do that. I'll show you how to use the derivative test. Applying the second derivative test in Calc 3 always involves computing these second partials. So we want to take the derivative of f of x with respect to x, and that's going to be some work. All right, we've got this expression here, and there's this massive product rule, and we've just got to gut it out. I'll show you in a minute how to check it in Sage, but for now I want you to be able to actually do these things by hand. So I'm going to rewrite fx down below here. In fact, let me see if I can make a copy of this. Oops. I think if I hold this down, yeah. Cool. All right, so just rewriting f sub x from up above, that's this guy. Alrighty, well, you know, there's nothing left to do but just roll up your sleeves and get after it. We'll take the derivative of this with respect to x, which is what? Negative 8xy times the second term plus this times the derivative of the second term with respect to x, and times the derivative of the exponent. Again, we see that the exponential factor can come out, and let's do that. So we'll have e to the minus x squared plus y squared times the quantity. Let's collect what's left behind, minus 8xy plus negative 2x times 2y minus 4x squared y. Definitely getting our algebra workout today. Let's expand out the stuff in the square brackets and see if there's anything that can simplify before we go on and do the other stuff. It turns out there's a little bit of simplification that we can do. We can combine the 4xy and the 8xy. And I'm going to check my notes here just to make sure I haven't made a mistake. Yes, I've made a small error here. When I distribute this negative 2x in here, I get an x cubed. So there is an x cubed here. And other than that, I think I'm good. Yep. All right, another bit of a symmetry trick here. If you don't want to grind your way through fy, just remember that the original function was symmetric in x and y. In other words, I get the same function if I switch x and y, which means I can get fyy by switching x and y down here. Switching x and y in the exponential, of course, makes no difference. And then down here we get 8y cubed x minus 12xy, because switching x and y there doesn't matter. So that saves us a little bit of work on fyy. Sadly, it doesn't save us any work on fxy. So we want to now compute the mixed partial, because remember, we're computing the discriminant, and the discriminant is fxx fyy minus fxy quantity squared, like that. So we need all of those second partial derivatives. So we go back up to fx, and we now take the derivative of it with respect to y. Let's do that. We get 2 minus 4x squared times e to the minus x squared plus y squared. That's the first part of the product rule. Plus 2y minus 4x squared y times the derivative of the exponential function with respect to y, pardon me, and we get this expression. As is common with derivatives involving exponentials, usually there's a common factor that we can pull out. So I'm going to pull out that e to the minus x squared plus y squared, and what's left behind is 2 minus 4x squared plus negative 2y times the quantity 2y minus 4x squared y. Again, let's expand this out and just see if there's any simplification that can occur. Great, we have 2 minus 4x squared plus the negative 2y hits the 2y, and we get negative 4y squared plus 8x squared y squared. Doesn't look like there's any additional simplification. So that's where we are with fxy. Everybody okay? Alrighty. Now for the classification process, we have our 5 critical points, and we need to first figure out the signs. So let's test all 5. We're going to test all 5 critical points. I'm going to label these A, B, C, D, and E. All right, so A is the point 0, 0. Well, we have to evaluate all of these functions at 0. So we've got fxx here. If we plug in x equals 0, y equals 0 here, we're going to get fxx is 0, we're going to get fyy is 0 minus fxy. If we plug in 0, 0 here, we're going to, all these are going to go away, but the 2 is going to survive, and we're going to have an e to the negative 0. That's a 1, so we're going to get a 2 out of this squared. And that's equal to negative 4, which is less than 0. What do we know about the discriminant less than 0? We know that it's the same. So we've just classified our first critical point using the second derivative test. Let's keep going. So b is 1 over root 2, 1 over root 2. And I've taken the liberty of plugging these values in advance. And what I get is negative 4 e to the negative 1 times negative 4 e to the negative 1. So that's fxx, that's fyy, minus 0 squared, that's fxy. So that's what I get when I plug in x equals 1 over root 2 and y equals 1 over root 2. What we see is that this is a positive number. This is positive. All right, so that tells me that there is concavity here. We need to figure out whether there's a local max or a local min at this location. How do we do that? So this tells me that there is a local constraint. How do we figure out which it is, a local max or local min? We go on and we look at the sign of fxx. If we look at fxx at this point, I already calculated it for you. It's minus 4 e to the minus 1. That's less than 0. If you go back and look at the second derivative test, this tells me that the thing is concave down. This must be a local min. I'm sorry, a local max. So we've classified this as a local max. You can continue with this process. It is a lot of work. Some of these exercises take a long time. In the third case, where we have this point, 1 over root 2 and negative 1 over root 2, we're going to get a positive discriminant, and we're going to get fxx positive, and this is a local min. I'm just writing out the answers. I'll leave them to you to verify. In the next case, we have minus 1 over root 2, 1 over root 2. This 2 has a positive discriminant, which means there will be a max or a min there. And if you check the sign of fxx, it's positive. And finally, the last critical point yields a positive discriminant, which means yes, it's a max or a min. I think it'd be somewhat satisfying to plot this function and just confirm that all of this work, these pages and pages of mind-numbing algebra actually yield sensible results. So I'm going to take this moment to jump over to GeoGebra and plot this thing. So we have 2xy times all right, and my scale is still all screwed up from the last one. I'll hold down the shift key, move the mouse onto the z-axis, and I'll pull up, and I'll pull up again, and I'll keep pulling up. The scale here is kind of in the other direction. Really have to kind of work to get any kind of visibility here. All right, we have this function with a couple of positive bumps and a couple of negative bumps. All right, I'm going to change the perspective here. I'm not a huge fan of this default projection. Okay. All right, we have a couple of positive bumps and a couple of negative bumps. That's consistent with our findings of two local mins and two local maxes. Let's see if they correspond to these points. If we look at them closely, we see that we have a bump in the first quadrant, plus 1 over root 2, plus 1 over root 2, and in the third quadrant, negative 1 over root 2, negative 1 over root 2. First quadrant, local max. Third quadrant, local max. Cool. And we have little bumps underneath in both the second quadrant and fourth quadrant. And that corresponds to these 2 points. What about that fifth critical point at the origin? That's right here. And you can see there are points near it that are above, and there are points near it that are below. This is neither a max nor a min, it's actually a saddle point. So this process, tedious and long as it is, has yielded sensible results for this particular function. Okay, one last thing. So you see that GeoGebra has confirmed this visually. I want to give you, part of what I've been doing in this class is trying to give you some tools to check hard calculations, because honestly, while I want you to be able to do these calculations in this class, because I think knowing how to do the calculations by hand is informative and rounds out your mathematical perspective, I also recognize that there are really powerful tools out there that let you do these calculations by automatically on the computer. The problem with doing things on the computer is it's incumbent upon you, especially if you're in a mission critical situation where the results of your calculation matter. They're either going to cost time or they're going to cost money if they're wrong. It's really incumbent upon you to confirm that what you're getting out of the computer is right. And I firmly believe that you don't really have the tools necessary to confirm that the results from a computer are right or wrong unless you've gone through this manual process first. You need that perspective in order to be able to look at the results of a computation with a skeptical and critical eye. So with that in mind, what I want to do is jump over to Sage, and I want to at least show you how you would do these calculations in Sage. So over here in Sage, let's redo a lot of these derivatives using Sage. I'm going to define the function that we've been working with all along. And let's just, oops, I didn't want to do that. Let's see what it looks like. Okay, that's our friendly function. And let's compute the first partials. F sub x, in fact, I just usually do fx, is the derivative of f of x and y with respect to x. And f sub y is the derivative of f of x and y with respect to y. And then let's just show, let's simplify these guys a little bit too. So simplify. And now let's show the results and compare them with what we did by hand. All right, there they are. Top one's fx, the bottom one is fy. Let's go compare those to what we calculated for our fx and fy. Here's our fx, 2y minus 4x squared y. There's our 2y right there, negative 2 times negative 1 times y. And there is our negative 4x squared y right there. And then the exponential function going along for the ride. So yay, we did it correctly. We can compute those second partials just as easily. I'll call it fxx. and that's just the derivative of fx with respect to x. And let's simplify as much as possible, and we'll copy that and do the derivative in y, and that's fy with respect to y. And then finally, let's do the mixed partial. That's the derivative of fx with respect to y. So there they all are, and we can show each of them. And we get that. Side note, you may wonder why I'm writing f of xy, parentheses xy here, and then I'm not doing that down here. There's a very subtle difference when you're using Sage, and it's not super important that we understand it at this point in our lives, but this fxy is actually an official function in Sage. And if I go down here and do something like f of 1, 2, it'll actually calculate the value of f at the point 1, 2. On the other hand, if I do f of x 1, 2 like that, and I hit enter, it's confused. The reason for that is this is actually a legit function, whereas this fx is really just an expression. It's just a collection of symbols involving x and y, and it has no idea how to evaluate it at a particular value. That said, we might desperately want to evaluate fx at a particular value, and we can do that, just not as easily as if we defined it as a function. We can use the substitute command and just say, look, I want to know what this expression fx looks like if I substitute x equals 1 and y equals 2. And notice the double equal sign here. What this is going to do is go through the expression fx, and everywhere it sees an x, it'll replace it with a 1, and everywhere it sees a y, it'll replace it with a 2. And if I hit enter, I get the partial derivative evaluated at 1, 2. So just a subtle difference, and if you're looking at this and you're wondering what's going on, that's what's going on. These are expressions, not functions. This guy up here is a function, and over here, when I type f of xy, it turns into an expression which gets differentiated, blah, blah, blah. All right. What can I do with these expressions? I can actually compute the discriminant now too. I'm ready to do that. I can say d equals fxx times fyy minus fxy squared. And I might even want to simplify that. And I might want to show it as a pretty expression. All right, there's the discriminant. And furthermore, I might want to evaluate it. So this 2 is just an expression. It's not a function. So if I want to evaluate it at one of our critical points, I have to use the substitute function. So I'm going to substitute x equals 0, y equals 0 into the discriminant, and I get -4. And that's consistent with what we calculated up here. When we plugged in 0, 0, we got -4, and we learned that 0, 0 was a saddle point. And that's consistent with what we saw in GeoGebra. Okay, continuing, we can go around robin here. We can look at 1 over the square root of 2 and 1 over the square root of 2 here. And we can see that we get a positive value, 16 over e squared. And furthermore, we can look at fxx at that point. In fact, let me just copy and paste. And we find that it's negative there. So that classifies the point 1 over root 2, 1 over root 2 as a local max. And is that what we did? That is what we got, local max. So again, using a computational device to do this kind of algebra for you can be a huge time saver. I do it myself, but I think it's dangerous if you don't have the background of doing these things by hand and really understanding what's going on, so that when you encounter a mistake, some kind of typographical error, you clear. Wow, that was a long one. All right, in problem 342, the goal here is to determine the extreme values and the saddle points for this function, and then use a computer algebra system. In our case, we'll use GeoGebra to graph the function and just confirm our results. Here we have a function of two variables, and of course, to find the extreme values, we first need to find the critical points. I guess before we do that, we should note here that the domain of this function is all of R2, in other words, all of the xy plane. There are no places where the function is undefined. There are no square roots of negative numbers or anything like that, so all real numbers. So to look for extreme points, it suffices to just look at partial derivatives and set them equal with respect to x is sine of y. The partial of f to y is x cosine y, and we want to set them both equal to 0. And I'll call that equation 1 and that equation 2. Remember to approach these logically. Both of these equations must be true at a critical point. So we'll start with the first equation and see what it tells us about the set of critical points. So equation 1 tells me that y needs to equal n pi. What does that mean? Well, it needs to be an integer multiple of pi. So it needs to equal n pi, where n is an integer, and we write this sort of funny bold-faced z to indicate the set of integers. To be even more explicit, we're talking about the set of numbers that maybe start like this. And it goes off infinitely in both directions. So we've got a large collection of y values that are possible from equation 1. What happens if we put these possible y values into equation 2? Well, assuming that y is n pi, then equation 2 looks like this, that to equal 0. All right, well, if you look at the cosine of, say, negative, let's start at 0. What's the cosine of 0? Cosine of 0 is 1. What's the cosine of pi? Negative 1. What's the cosine of 2 pi? 1. 3 pi? Negative 1. Let's go in the other direction. Cosine of negative pi? Negative 2 pi? Negative 3 pi? And you see a pattern here. In fact, we can actually replace the cosine of n pi with the expression negative 1 to the n power. When n is 0, negative 1 to the 0 is 1. When n is 1, we have pi. Cosine of pi is negative 1. Negative 1 to the 1 is also negative 1. So this is a replacement for the expression cosine of n pi. Why have I done this? Essentially to show you that this part expression is never 0. So equation 2 then requires us to set x equal to 0. The only way that we're going to get equation 2 to be satisfied, given the information that we received from equation 1, is for x to be 0. So the set of critical points is of the form 0 n pi, where n is an integer. Let's try to classify them. How do we classify? We need to apply the second derivative test to each of these points, 0, n pi. Well, to compute the second derivative test, we of course need all of these second partial derivatives. The partial of fx with respect to x is conveniently 0. Fy with respect to y is what? Negative x sine y. And fx with respect to y is cosine of y. If we compute the discriminant, fxx times fyy is 0 minus fxy quantity squared, that's cosine squared y. If we substitute in the value for y for each of the critical points, we get minus cosine squared cosine squared n pi. That's minus -1 to the n. Using this earlier identity, we know that cosine of n pi is really -1 to the n. And that's squared. Well, -1 to the n, it's either +1 or -1, but when you square it, it's going to be 1. So this is going to result in just a -1. That's less than 0. And we can conclude that all of the CPs, all of the critical points, are saddle points. All right, let's hop over to GeoGebra and have a look at this mysterious surface and see if it's consistent with the results that we've just come up with here. Wish I could figure out how to make the default projection here perspective instead of orthographic, whatever that means. Anyway, x sine y, I think that was it. Let me see here. Yeah, x sine y. All right, we get this relatively complicated looking surface. Let's orient ourselves here. This is the positive x-axis, this is the positive y-axis. We know that all of the critical points have x equals 0, so that means they're on the y-axis. And furthermore, the y-coordinate is just multiples of pi. So I think I can rescale this a little bit to get a few more pieces in here. Let's go out and look along the y-axis at first of all at 0, 0, which is one of the critical points. It's clearly a saddle point, right? We see part of the function below, part of the function above, and at the origin here, we see function values that are above and function values that are below. If we go out a multiple of pi, what's a multiple of pi? That's a little bit more than 3. That's right here. We see another saddle point. If we go out a multiple of 2 pi, we're out here a little bit past 6, another saddle point, and so on. And in the other direction, if we go out a multiple of negative pi, here, saddle point, and negative 2 pi, here, saddle point. They're all saddle points, and they all lie on this y-axis. All right, in problem 344, probably one of the longer exercises of this set, we're asked to find the absolute extremes of the given function on the indicated closed and bounded set R. All right, the first thing you want to do is sketch R so that you understand what's happening. So I'm going to sketch R here. By sketching the vertices, let's see, let's do this in red. So we have a point here at 0, 0. We have a point up here at 0, 4, and a point out here at 1, 2, 3, 4, 5, 5, 0. And the domain is the interior and the boundary of this triangle. That's the set R. All right, what's our goal? We were given this function xy minus x minus 3y, and we're asked to find the absolute maximum and the absolute minimum of this function restricted to this domain. So if I am taking xy values from this red set and plugging them into f, what's the largest possible value I can get from f, and what's the smallest possible value? This is, as we've discussed earlier, is divided up into roughly two parts. The first part is to find possible maxes and mins on the interior. So part one is to find the critical points on the interior of R. And by interior, I mean the part inside the triangle, excluding the boundary. And then the second part will be to find maximums and minimums around the boundary, and then we'll group all of these maxes and min values together and compare them. So let's go through this first part. So finding critical points on the interior of R, Fermat's theorem applies, and we can simply set the partial derivatives equal to 0, or in other words, set the gradient equal to 0 and find critical points. Setting the gradient equal to 0, we have f sub x. The partial of f with respect to x is y minus 1. F sub y. The partial of f with respect to y is x minus 3. And of course, we want those to be simultaneously 0. This yields y equals 1 and x equals 3. So we get one critical point, 3, 1. And we can actually plot it here on our figure. All right, the green dot is 3, 1. And indeed, we could even compute the value of f there. The value of f at 3, 1 is, let's see, 3 minus 3 minus 3. Looks like it's minus. So we'll make a note of that here, that at this point, the function value is minus 3. That's the only information that we get by looking at the critical points. We could go on and actually classify this thing. In fact, let's do that just for practice. Let's classify the point 3, 1 by computing the discriminant. The discriminant is fxx, which is 0, times fyy, which is also 0, minus fxy squared, which is 1 squared. That's less than 0. This is a saddle point. So it's not a max or a min. So we don't even really have to think about this one. So that means that the maximum and minimum of f restricted to this red triangle R must lie on the boundary. Some point or pair of points or some points on the boundary let us achieve this maximum and minimum value. So that brings us to the second part of this exercise. We need to look for extreme points on the boundary. All right, I'm going to label the various sides of the boundary because each has a slightly different mathematical description. And we'll take each of them in turn and we will figure out what's the maximum of f if I just restrict myself to this line segment along the x-axis that's part of R. What's the maximum and minimum of f if I restrict myself to this line segment along the y-axis? And finally, what are the max and min values if I restrict myself to this hypotenuse, side 3? We'll take each of them in turn. Along 1, we know that y is equal to 0 and that x is between 0 and 5. So why don't we take those assumptions and plug in functions. So we'll x for x and just remember that it's between 0 and 5, and we'll plug in 0 for y. If we look at the original form of the equation, anything that has a y in it is going to go away because y is 0, and the only thing that remains is negative x. What's the biggest value that negative x can take if we restrict ourselves to the interval 0 to 5? Well, the biggest value occurs at x equals 0 and is 0, and the smallest value occurs at x equals 5 and is -5. So let's label those on our diagram. So here, the value of the function is 0, and here, the value of the function is -5. All right, let's keep collecting those important values by examining side 2. Along side 2, we have that x is equal to 0 and y is between 0 and 4. Let's repeat the process by substituting what we know into x. So along this line segment 2, x is equal to 0, y will just let equal y, but we'll remember that it's between 0 and 4. And then let's go up and see what happens when we stick x equals 0 in. Anywhere that has an x is going to go away. So x, y, and x go away, and we're left with -3y. Great. This will be biggest at y equals 0 and is 0, and smallest at y equals 4 and is -12. So let's collect that information and put it into our diagram. We're reassured down here that it's 0 because we found that the function value was 0 along this segment here. It's also 0 along this segment. So that's a reassuring mathematical consistency. It tells me that I'm doing my algebra correctly. All right, the last side, somewhat more complicated than these previous two, is the hypotenuse side. And here we simply have to come up with the equation of the line. So we need the equation of the line through so if we have 2 points, we're going to have to figure out the slope. The slope is just pick a rise over a run, so we'll look at 4 over -5. So the slope is -4/5. And then use, it doesn't matter, use either one of these points in the point slope formula. So let's use 0, 4. We have y minus 4 equals -4/5, like that. Or y equals -4/5 x plus 4, like that. All right, let's take that and substitute it in. So what do we know now? We know that x, 0 is less than or equal to x less than or equal to 5. So, right, we're trying to describe this hypotenuse mathematically, and along this hypotenuse, 0 is between 0 and -5. Sorry, x is between 0 and -5. And y has this expression, 4/5 x plus 4. So we're kind of just stuck with the x, so the x goes along for the ride, and everywhere we see a y, we're going to replace it with this expression for y. So reminding myself here, we have x times y. So x minus x minus 3 times the quantity, -4/5 x plus 4. In other words, everywhere I see a y, I'm replacing it with the equation of this line. You can simplify this a little bit, and I've done so in my notes, so I'm going to cheat a little bit and look over at my notes here. If you simplify this, you get -4/5 x squared plus 27/5 x minus 12. So that's what f looks like along 3. Well, somewhat unexpectedly, we want to find the maximum and minimum value of this function. We're now back in Calc 1. We need to sort of do an optimization problem within an optimization problem. In other words, we'll call this function g of x, and we'll figure out what its maximum and minimum values are on the interval from 0 to 5. How do we do that? Take the derivative of g and set it equal to 0. That's minus 8/5 x plus 27/5, and we set that equal to 0. And we learn that x is equal to, and I've done this also, we get x equals 27/8, like that. That's a critical point for the function along this boundary. Again, a calculus problem within a calculus problem. All right, what's the value of g at this point? Let's see here. So we want to evaluate g at 27/8. I'm going to pause here and go calculate that. All right, not the prettiest number that you'll ever run into. It's, let's see, negative 231 over 8, ultimately, or in fact, probably exactly, negative 2.8875, negative 2.8875. And let's just also get a grip on what 27/8 is. 27/8 is 3.375. I'm only really recording these so that we can identify this point on our figure. So, and I guess there's one more thing we should check. What is, and I'm going to go pause and calculate that. So let me. Okay, so what's the corresponding y value for this x value? We can figure that out by plugging 27/8 into the equation up here of the line. And according to my calculations, I get 13/10, which is 1.3. So we now have all the information we need. We want to plot the point 3.375, 1.3. So 1, 2, 3.375 and 1.3. So that's, again, just, of course, it's on the line, right? By design, it's on the line. So we have this sort of unfortunate arrow in the way. And I can't get rid of it really, so we'll just make it, we'll turn this into, let's have that arrow there, and we'll put this dot here, and we will note that the value here is, what did we decide the value there was? Negative 2.8875. So right here, negative 2.8875. Observe that that value is higher than both negative 5 and negative 12. We should also check the boundaries. Of course, we don't really need to check the boundaries. If we've done our work correctly, then we know that g of 0 so the boundaries of the interval 0, 5, g of 0 is 0. I'm sorry, g of 0 is going to be negative 12. And g of 5 is going to be, looks like negative 5. All right. We are now ready to answer this question after a lot of work. We looked at the interior, we looked at the boundary. It remains to just compare all of these values to each other. Note that since this is a saddle point, we don't really need to think about it. And let's go around and look at all the rest of the points. So of all of these special values that we've identified in green here, which one is the largest? F attains its maximum. Zero. F attains its minimum on R. Where does it attain its minimum? It looks like negative 12 up here at the point 0, 4 and is negative 12 there. Now, are there larger and smaller values of f if we go outside of this triangle? Absolutely. But it's very often the case in applications that you have a restricted domain, and then the question is, what's the biggest possible value on this restricted domain? What's the smallest possible value? We now have the tools at our disposal. In this section, we learned about setting the gradient equal to 0 to look for critical points and then find possible local maxes and mins. And then back in Calc 1, we learned how to maximize functions along straight lines like this. So putting that information together lets us answer this question. Let's put a nice big rainbow box around that because that was a lot of work. All right, one more problem. Oh, you know what? I actually built a GeoGebra. Demonstration of this thing, and maybe I'll go pull that up just to give you a visual of what this looks like. So let's go to the 3D calculator. Let's open here we go. Alrighty. Well, here's the surface, the original surface that we're talking about, and sitting in the XY plane, let's orient ourselves. Here's the positive x-axis and the positive y-axis. Here is that triangle sitting in the XY plane. And the dotted line is that triangle as it is projected onto the surface. And we look at the values. So the curved looking triangle here is really telling us the values of the function at every point around the boundary and inside. And we can see that there is this critical point, which I've put right here. It's a critical point, but it's a saddle point, so there's no maximum or minimum there. So that led us to exploring the boundary. We can see that along the hypotenuse, there is a local max along the hypotenuse right about here, and we found that local max. And then it drops down in this direction and drops down in this direction. But it turned out that that local max along that part of the boundary was not higher than the value of the function over here at the origin. So even though it was a local max, it didn't turn into a global max. So the global maximum, if you look carefully at this thing, occurs over here at the origin. And the global minimum, the lowest point in the domain, is down here at this vertex. And just in summary, the global max is here at the origin, and the global min is out here at 0, 4. All right. Now let's carry on with the last exercise of the day, exercise 356. Another somewhat applied problem. This is something that shipping companies actually do. They put constraints on the shapes of boxes that they're willing to ship. And here we have some fictional shipping company that handles rectangular boxes. And it will accept these rectangular boxes provided the length, width, and height of the box does not exceed 96 inches. Let me just sketch that for you so that you can see what's being talked about here. Looks like I'm not going to get a cube there. I'll just draw my own cube, I suppose. So here's some shipping box, and it's going to have a length and a width and a height. Doesn't really matter which side I call length, L, W, or H. What are we asked to do? Well, given the constraint that the length plus the width plus the height must be, not equal to 96, but less than or equal to 96. What's the largest possible volume? What's the volume formula for this? We learned this one a long time ago. It's length times width times height. All right, we're asked to maximize the volume. And the volume function is a function of 3 variables, and we haven't really talked about that. Mostly we've talked about maximizing functions of 2 variables. So how are we going to sort of get our hands on a function of 2 variables to maximize? We're going to use this, what we call the constraint function. So this constraint says that L plus W plus H must be less than or equal to 96. Now, if we're asked to find the largest possible volume, it seems reasonable, I'm not going to prove it, but it seems reasonable that we need to max out this constraint. We need L plus W plus H to equal 96, right? Because anything less, we're not going to be able to get the largest possible volume. Well, if we take that into account, then we can solve for H as 96 minus L minus W. And then we can substitute that into the volume function. And now we have a function of 2 variables, L and W. Before we carry on, it's probably a good idea to figure out what's the domain of V. So the domain of V, it's somewhat challenging, but we can make at least a rough estimate, right? We know that if we just look at V on its face, it has no singularities, no negative square roots, no nothing. So nominally, the domain of V is all of LW space. But there are some constraints. We know that, for example, no individual dimension can exceed 96. So let's put a 96 here and say a 96 up here, right? Certainly the biggest possible value L could be is 96. So if L is 96, oh, and they're positive. So everybody's positive. L, W, and H are all non-negative. If L is 96 and we're worried about this constraint, that's going to set both W and H equal to 0, right? So, and what's the volume of that? Well, if you do the volume calculation, you're going to get 0. So you're not going to get much out of that. So why don't we at least allow for the possibility that L plus W is equal to 96. And even that is sort of overshooting, right? So if L plus W is 96, right, what's H going to be? Go back to the constraint. H is going to be 0. What's the volume going to be? Still 0. So this domain is still an overestimate of the full domain, but we're going to just stop with this domain and use it. And if we can find the maximum of V on this domain, it's going to coincide with the maximum of V subject to the full constraint. So let's carry on here. So that's the domain of V that we'll work with, and we'll maximize it on this domain. All right. So potentially we're going to look for maximums and minimums. We want the absolute max, absolute min on this domain. But we know that if we look at the three sides of the domain, that V is 0 along 1, 2, and 3. So this is a lovely thing because we know that we can find, for example, if we take L equals 1, W equals 1, and H equals 94, the volume of that box is going to be 94 cubic whatevers. So already we know that any point inside this domain is going to be better than any point on the boundary of the domain, which always gives 0 volume. So this relieves us of having to do all the work that we did in the previous problem where we're worried about maximums and minimums occurring on the boundary. We can just work on the interior, use Fermat's theorem, find critical points, and then start comparing the values. So let's find critical points in the interior. We do that by taking the gradient of V and setting it equal to 0. The partial of V with respect to L, and I've done a lot of this work in advance because I'm now trusting you to be able to take partial derivatives. So I've done this in my notes in advance. The partial of V with respect to, it looks like I did W first, is 96L minus L squared minus 2LW. And the partial of V with respect to L is 96W minus 2LW minus W squared. And we want to set that equal to 0. And there's nothing obvious about how to solve this. It would be hard to isolate a variable here, and we don't see any obvious cancellations. But there is one thing that we can do. Because we're assuming that we're working on the interior of this domain, we know that L and W are not equal to 0. That lets me divide out the common factor of L in the first equation and the common factor of W in the second equation, and it's going to make this a little bit easier to work with. So 1 now becomes 96 minus L minus 2W, and 2 becomes 96 minus 2L minus W. Now we actually can solve this either by solving for one variable in terms of the other, or by adding, by multiplying and adding. I'm going to leave that to you to figure out, but I will. I've done the work in advance, and if you go ahead and solve this system of equations, what you find is W equals L equals 32. So there's one critical point, and it's the point 32, 32. Because there's only one critical point, and because we know it's 0 all around the boundary, we can conclude that this is a local max, and in fact, it's actually a global max. It's global max. And we can also learn that H is equal to 32 in this case, and that the maximum volume is 32 cubed. All right. If we went up here and plotted this, we would be looking at about 1/3 of the distance in each direction That is where the critical point is. That's 32, 32. And that's where we've maximized V. It goes down to 0, right? As we go from here, the function values go down to 0 as we approach the boundaries. So this is just a bump sitting above this triangle. All right, so there's an application. For suggested exercises, I want you to look at all the exercises and make sure that you focus on the algebra and the logic of finding critical points as I demonstrated here. And when you feel comfortable, go ahead and jump over to the web work and do the assessment for Chapter 4, Section 7. Thanks.